Okay, let's continue with the electrostatic potential in cylindrical coordinate system or further application of Bessel function in solving electrostatic potential. So we have seen that once we organize the roots of Bessel function uh, specific order to a given interval, and then we can happily use them as to satisfy specific boundary value uh, boundary values. So closely related concept is Fourier-Bessel series. We have discussing the Bessel function as an orthogonal function. Let's start with the Bessel ODE, which is now you are all familiar with, and it is written here. And then for simplicity, let's take the interval uh, in which we are interested in solution be a to b. Now let's say that x is equal to kappa times rho. This comes in the physical application. We have seen is that in the cylindrical coordinate system, rho is the radial coordinate, and then x turns out to be a kappa times rho, where kappa comes from the eigenvalue along z direction. But irrespective of that, we can use it as a conventional Bessel function given in this equation. But for a physical problem, we would need a form of this in which rho directly corresponds to the cylindrical coordinate system. Now we can have a solution, Bessel function, Newman function, or Hankel functions of first and second kind. Those are considered based on the physical problem or depending on the boundary condition or the region you want to handle. For example, we know that if 0 is in the domain, then we can't use the Newman function, then we can have to use only Bessel function, and then we have a similar problem with the Hankel function too. So it is depending on our physical problem we can see them, but we want this to satisfy Sturm-Liouville boundary problem. When we express this differential equation in the self-adjoint form, we have a one minor modification. We have a weight function which is appearing here. That would be obtained by comparing this equation, and then we have a differential equation rewritten here, which we call is the weight function rho, and by comparing the differential equation we have a p of rho is also equal to rho, and then this is our eigenvalue. Just to remind you about the Sturm-Liouville boundary problem, let's say rho 1 and rho 2 are a given region. We want to, and then to satisfy Sturm-Liouville boundary problem, the following entity have to be 0. The P of rho in terms of y1, y2 prime minus y2 prime, y1, and evaluated at the boundary of the our domain. Now, if we choose rho 1 to be 0, then 1 because of P of rho itself is 0 on the boundary rho 1, the Sturm-Liouville boundary condition is naturally satisfied. It's a trivial uh, condition with the P of rho equal to rho itself. However, we have a problem at the other boundary, that is when rho is equal to rho 2. We have seen that the Bessel function does not satisfy this very easily. But to satisfy Dirichlet boundary condition, we want y1, y the solution to be 0 at rho is equal to oh, rho 2. So, in order to satisfy this boundary condition, the easiest way what we do is we have done in the earlier case, we simply find out the roots of the Bessel function J nu and scale them into your problem such that all the values of k nu alpha is scaled to rho 2 equal to a, and then uh, you choose the roots of the Bessel function, and then we have the Dirichlet boundary condition is naturally satisfied, and then we can express any function in terms of the uh, Bessel function. But we Okay, once we choose the values of the roots of the Bessel function, we can simply scale them k nu n a equal to n alpha, and then we can easily satisfy the Sturm-Liouville boundary condition, and the eigenvalues in this case are given by the k nu n or kn for a given Bessel function of the order nu, and uh, we have now we can use the function j nu alpha nu n x a as an orthogonal function. Mind you that this is only one order of the Bessel function used at a time. It is not that the nu is equal to 1, 2, 3, 4, 0, 1, 2, 3, 4 is used as a Bessel function. It is that the Bessel function of the order, let's say, 0, or with the scaling done with the root nu alpha in the interval a for a different n is used as an orthogonal function. The same thing can be done for the j0, j1, j2, etc. So j nu uh, the function connected with the roots of the Bessel function together acts as an orthogonal function. However, normalization need to be done in this case, and it can be easily shown that the normalization is basically given by nu plus 1. There is an error here. So it can be shown using the properties of Bessel function that this integral corresponds to the value of given here. So for a given function f of x in the if it is L2 function in the interval 0 to a for a positive value of a, we can express it in terms of Fourier-Bessel series is given by this, and the coefficients of the Fourier-Bessel series can be computed using this equation would completely describe the function in terms of Fourier-Bessel uh, series. Now we have seen that if we use J0 as our preferred Bessel function, then we map the roots of the J0 and then use in the interval 0 to a, and then use them as a basis function. On the other hand, it may, sometimes J0 may not be convenient, then we can use J1 as our basis function, and then we have to map all the zeros of J1 in the interval 0 to a, and then use them as a Bessel function. Let's look at the example, a quick simple example. Again, we have a function rho phi defined in a circular region. This could be top of your cylinder, which we have been doing in an extended problem with the radius a, which satisfies the condition that the v of rho equal to a for all phi is equal to 0, and then we have to the problem is that we have to express them in terms of orthonormal function. Now, when it comes to variable phi, we know that it is easy to express them in terms of the Fourier-Bessel function, Fourier series. And when it comes to row variable, we have to use Fourier-Bessel series. We first use J0 as our preferred basis. In fact, we can replace J0 by any of the higher order Bessel function J row. But let's see that in this case we write phi the two coefficient correspond, first one corresponds to Fourier series and second one corresponds to the Fourier-Bessel series. Uh, in the above, alpha 0 n is the nth root of Bessel function J0 rho, and am can be computed with the standard formula. The first one is from the uh, Fourier series, which uh, we can compute, and the second part is coming from the uh, uh, Fourier-Bessel series, as we have seen in the earlier slide. In this case, I uh, m phi is missing, so that we can compute the Fourier series. Now we can use any other instead of this. In this case, let's say that we want to not to use J0, but we can use a arbitrary or higher order Bessel function. Then we can use it as a J nu as your basis function. Then we can expand them in terms of this as given here, except that only this changes, and then we have the coefficient. We have a j nu plus 1 here, and then again here also e to the power I m phi is missing, and this is how one computes the uh, Fourier-Bessel series for a given arbitrary function. And now we can completely solve the problem of cylinder placed at the different potential into we have broken the problem into different pieces because of the differential equation is new and somewhat difficult one. Bessel function is not as simple as the other earlier equation which we have seen.